But without further ado, I'd like to invite Thomas Schön, who's going to talk about control views on reinforcement learning. Thanks.
Thank you. Thanks a lot, Carl. All right, so what I'll talk about today is modeling of dynamical systems and how you can learn these models. And this is joint work with a bunch of people. So Roger, who used to be in Cambridge at the time, Mike Jordan at Berkeley, Fredrik Lindsten in Uppsala, and then Carl here, and Arno and Simo at Auto, and Andreas, one of my students back in Uppsala. So then, what's a dynamical system? So in a short sentence, it's something evolving over time that has a memory. That's a dynamical system. Here are a few examples that I've been working with and still work with. So the Swedish fighter aircraft, it's moving around at high speeds in 3D, clearly a dynamical system. Human body capture, I'm going to use that as a little example. So as I move around, I'm a dynamical system. Depending on the speed I have, I will move in different ways. Cars, autonomous these days, and active safety. This was the Volvo company that I used to work with. Nowadays I work with Autoliv, which is a Swedish company that they invented the seat belt and the airbag, and now they're moving into active safety. Or if you want the textbook version of it, that's what it looks like in terms of a graphical model. So you have some hidden, unknown, latent states. They will be blue here. I call them X. So you can't measure them. So imagine human motion capture. When I move around, you can't directly measure typically the position and orientation of each segment. But instead you measure something else. I'm going to use inertial sensors where we measure accelerometers and acceleration by accelerometers and using gyroscopes for angular velocities, and that's the y's, that's the observed variables. And the problem then becomes to find the blue based on the black. And also we have some unknown parameters in our model. So this is how we typically write it down, depending on where you come from. But if you look at the left, so this is a nonlinear state space model in discrete time. So we measure the y's, and we want to find the parameters describing this model, the red things, the thetas. And in doing that, we typically also have to find the states, whether we want them or not. So in terms of the full probabilistic model, you can write that down as the data distribution, or the likelihood, if you like, and a prior. And we can then put that together a bit further to see the full structure of this model. So this you can deduce either from the equations using the Markov property and Bayes rules and a few lines of equations, or you can start just from the graphical modeling point of view, depending on what you prefer. But it shows you the structure of a nonlinear dynamical system in a nice way, I think, in terms of this full probabilistic model. So you see where the observations comes in, and you have the dynamics and the prior. So when I talk about the model here, I mean a probability distributions. We express everything in terms of probability distributions. And again, the aim here is to build a flexible model and to compute the posterior distribution of that flexible model that is capable of describing any nonlinear dynamical system. So that's a fairly big goal, I would say. But I'll show you one, as far as I think, a fairly practical way of doing this. And then again, it's this posterior distribution that we're looking for, the distribution of all the hidden, latent, or unknown, or missing, or whatever you want to call them, the blue things here, the states at all time, and also the thetas describing the model, conditioned on the measurements. And then you can just separate that into the state estimation problem and the parameter estimation problem, if you like. So just to give you an example of what are these blue and red and black things, I'm going to look at motion capture just to make these equations come alive a bit. So we want to compute the position and orientation of the different body segments as someone is moving around. And the unknown parameters theta here, they describe the body shape. So what's the distance between my hand and the elbow and the upper and the shoulder and so on. And the measurements we have access to here are accelerometers, gyroscopes, and this is indoors. And accelerometers and gyroscopes, they are relative sensors, so they can never measure the absolute position. So you need to that's why you have a GPS in your phone, if you have a smartphone. So here we have an indoor GPS type system based on ultra-wideband to compute that. And let's see if we have, I'll just show you what this looks like. So you see the person moving around, and then we solve this as an optimization problem, and I'll just show you the point estimate here. That's the skeleton glued on top on this person as he's moving around. So as you can see, the positioning is not perfect, but it's definitely enough for gaming and movie industry, for example, that have been using this. And as you can see, even though we don't have line of sight, we can still see what this person is doing inside this little box here. All right, so that was just to give you one example of a dynamical system. If you want the slides, by the way, they are on my website already, so you can just go and have a look there. All right, so let's switch back. So that was a bit of a background what I mean by dynamical system and a few equations and an example. So what we're going to do now is to move on to construct a model which is based on a Gaussian process and the state space model. So this idea has been around for a while. Why is this interesting? Well, this is I think one of the key lessons that we've learned in machine learning over the last couple of years, that these flexible models, they do give the best performance. And that basically, there are a few different ways. The deep learning is highly popular, so I'm not going to do that today. I'm going to do Bayesian non-parametrics instead via the GP. So the idea is the following. So now we move away from the parameterized form, since we're doing non-parametrics now. So we place a GP over the unknown functions f and g, and then we will try to infer that. And we look, everything that's red, that's part of the parameters that we need to compute. So we need to compute this posterior distribution. And that's completely impossible to do in closed form. So whether you like it or not, you're forced to some form of approximation. So I'm going to talk a bit about how we can use particle filters to solve this. And in fact, we use a particle filter inside a Markov chain Monte Carlo algorithm to solve this. You can also do this using variational inference. Carl has a solution like that. Interestingly, they are roughly the same in terms of computational cost, which I find interesting. Our first work on this was back in 2013, and then Roger's PhD thesis gives you a nice overview of GPSSMs, I would say. All right, so we can't use the standard GP here, so we need an approximation of some form. So I'm going to use this. This is something I borrowed from friends in Helsinki, Arno and Simo. So you use what's called a reduced rank approximation, which means that we approximate the GP using an infinite series expansion. And if you choose the basis functions in this way, on the slide here, we don't have to dive into those details here, and let m tends to infinity, then this is a GP. So why is this an interesting construction for this particular problem? Let me just cartoon way convince you that or indicate that might be a GP actually. So if you have the situation on the left there and you use 4 basis functions, it's not really doing very well. You're up to 9, it's better, 16, it looks quite all right. This is still just one dimension. But why is this a reasonable approximation for us? Well, if we look at the learning problem that we need to solve, that's when we see why this makes sense. So this is where we started. Just put a GP on F. I'm going to skip G now. You can put it on G as well, but that's just duplicating the same thing more or less. So when we use this approximation for the GP, then you get this series expansion basically. That's what you get. And if we look at that, it's actually linear in the red things. It's linear in the parameters, and it's still nonlinear in the states. So that's still challenging. But this is good because and we want to do full Bayesian learning of this. And since it's linear in the parameters and we have Gaussian noise on top of this, we can just use closed form conjugate updates for that. That's just the matrix normal inverse Wishart relationship, which we can just write down. So it's still nonlinear in the states, and that's where the particle filtering solution comes in, because we can estimate the state arbitrarily well using a particle filter. Hence, we will have something that actually converge to the true solution as you up the number of compute. So again, very briefly, the learning problem that we're faced with, we need to compute this posterior distribution or some marginal of it. This amounts to high-dimensional integration or optimization problems, depending on how you want to set it up. So we're going to opt for the integration solution to this. And this is where sequential Monte Carlo comes in. So let me just ask you, how many of you have implemented a particle filter or a sequential Monte Carlo sampler? 1, 2, 3, 4, 5. Yeah, so a few. So for those, so that's great. I'm glad to see that. So for those of you who haven't, I'll give you a brief micro on what sequential Monte Carlo is. It's something that you can use when you need to solve a hard integration problem where there is a sequential structure present. So in our setting here, the sequential structure is super clear, I hope, so since we're evolving over time. But it's more general than that, actually. So again, the theta is rather straightforward here. We can do that in closed form. The blue things, the states, is still very challenging. So what I'll do now is to step back a few steps and just give you the idea behind SMC in a rather general fashion. I'm not going to look at the actual algorithm, but I'll try to give you the intuition behind it. And depending on the time I have, I will also spend some time on the actual combination within MCMC, just also on a high level. So this is what SMC is in a very abstract problem formulation, I would say. So we're looking for some target distribution. For example, in our setting here, we have the joint distribution of all the states and all the parameters conditioned on the measurements. And then what we're going to do is we're going to sample from a certain sequence of target distributions that's defined on some space of increasing dimensions. And then, as usual, we can write this as the unnormalized over normalization constant. And then we require that we can evaluate this unnormalized density pointwise. And the normalization constant is typically quite challenging to compute. And why would we be interested in a problem like this? Well, for example, might be interesting just to find the normalization constant in certain applications, or you want to approximate the target distribution, or you want to solve some integral with respect to that target distribution. So an important question here is, how general is this problem formulation? I would argue that it's actually extremely general. And I'll try to substantiate that to some extent. At least it covers all nonlinear dynamical systems, but it also covers quite a few other things. So again, this target distribution, we can build that in quite a few different ways. And the most basic construction comes from these chain structured graphs, like the one we have in a nonlinear state space model. And then the target distribution is now if we look at the filtering problem, so the distribution of all the states up till time t, condition on all the measurements up until that time. And then remember, we required that we should be able to evaluate the unnormalized distribution pointwise. That's in this case just given by the model, and we can always evaluate the model here. So that's all good and fine. The normalization constant is still challenging to find. So this fits the general problem formulation we just set out. And what the particle filter does, or the sequential Monte Carlo sampler does, is that it provides you with an approximation of this filtering or smoothing distribution for the nonlinear dynamical system. And it does that by maintaining an empirical approximation made up of typically a quite large number of samples, and each sample has a weight associated to it. And what it offers is a systematic way of exploring the state space, I would say, in a nonlinear dynamical system. So let me give you just one example where we use this for indoor positioning. Again, I won't give you the algorithm, but I'll show you how it works. So here we have the problem, a person is moving around indoors with a little, like the hotel cards we have here, slightly thicker, you see it on his waist there, with some inertial sensors, a magnetometer and a radio in it, and then you want to compute the position of this person as he or she moves around indoors. And we also have a map of the buildings. Nowadays we have maps of more or less everything, so that's fine, I think, in terms of an assumption. And we're representing this map as a probability distribution. So if you look on the right-hand side there, so that's clearly not the Gaussian distribution, but that's all right. We can work with any distribution, whatever name it has. So that's an office building. It's just saying that with probability 1 I can move around inside the office, but with probability 0 I'm going to move through this wall. So that's just the thing we're saying. So let's have a look at what happens if we do that. So before I start, I'll just show, up here you see Johan, the student who did this, as he moves around in the office environment. Down here you have the map, and each little blue dot here is one particle. So the state space here is position in 3D, velocity in 3D, and heading. So it's 7 dimensions. I'm not able to plot that, but I can plot 2 or 3, but I'm plotting 2 here. And the little green thing here, that's more or less the true position. So we initialize using a radio. That's why we have a sphere, because that's highly uncertain, but it gives us at least some understanding. And then as this person moves around, let me pause for a second. As this is what you did before you had GPS. You brought up a paper called a map, and then you looked at that, and as you moved around in a new city, you watched the buildings, and after a time you could lock in and see where you were. This is exactly the same principle. This is also what we used for the fighter aircraft to solve the navigation problem there. And here we do it for person moving around indoors. So after this person has made a few turns, that's the way you excite the problem, if you like. You know better and better where you are. So what you see here, the blue thing, this is now the filtering distribution. And this might also be an interesting place to pause and just to make the case that it's, at least in this application, really important to maintain the entire distribution. If you extract just a point estimate, which is fine if you know what you're doing, but if you do that here, let's say you select the mean value, which is common, I guess that would be somewhere around here, where you know with probability 1 that you will not be. So if you extract point estimate, make sure you know what you're doing. That's the take home from that, I guess. Since we have the full an estimate of the full distribution here, we have still not extracted a point estimate because we're too uncertain about where we are. But after this little turn here, there is just one cloud left, and you will see a little black snake emerging as well, which is the estimate from the filter. And after this point, you'll get the position accuracy of a meter or 2 as you move around indoors. And then here, as we move here to the open space, then uncertainty grows in the lateral direction. Then the model comes in and removes that uncertainty again. Okay, so that's just one little example of what you can do with the particle filter. But then, a bit provocative maybe, so this nonlinear state space, I mean, that's a challenging model to work with, but that's just a special case, especially if you view the graphical model of it. It's just a chain. What if you want to do something else, like a lattice or a tree or whatever? Can you still use this? And yes you can, because you can still build up an artificial target sequence over these models. And if you do that, then you can apply SMC to these models. And then all of a sudden, when you do that, you will also drag with you all the convergence results that exists for SMC. And you get guarantees for models like this, which I find quite interesting. And I think that's quite possibly a severely underutilized idea. I should also say that these methods are computationally quite expensive. But again, the nice thing is they come with some theoretical guarantees. We've done a few things on graphical models and also for more high-dimensional spatio-temporal models in those two papers, and there are a few other things happening as well. All right, so let me just briefly sketch what we need to solve our problem here, because the particle filter itself is not enough. So what can we do? Well, 7 years ago now, there was a beautiful paper published in JRSSB, I'll give you the reference soon, about showing you how to combine SMC within MCMC, which is, well, computationally a bit brutal at times, but as a theoretical construction, it's really beautiful, I think. So why would this be necessary for us? Well, if you think about the target that we have, that's the joint distribution of all the states and all the parameters given the measurements. That's a very high-dimensional beast, if you like, to figure out. So just running a standard Metropolis Hastings or Gibbs on that will simply not be feasible. But if you think about it, what we have now with SMC, that's actually, you can view that as a way of building up a high-dimensional proposal mechanism on this huge space of state trajectories. So that is indeed a huge space, but it's a space with a lot of structure, because we have our dynamical model telling us how to move around in this space. And the SMC algorithm gives you a way of transforming your measurements into that state space. And a bit more precise, what you do is you build a Markov chain that has the target distribution we're looking for as well as a stationary distribution. So you can also use this for parameter learning if you want. And that's the paper by Christopher and Roman that shows you the basic idea and proves that it's actually a valid construction. And it comes with a funny name of an exact approximation. But it's a pretty good name here, because it's exact in the sense that you will get samples from this target distribution. It's approximate in the sense that in computing this, we're using a particle filter with a finite number of particles, which will always be an approximation. But theoretically, that's still a valid construction, which is not intuitive, but true and pretty cool, I think. So let me, I'm going to skip a few things here. But if you want to, okay, so if you want to set up, let's do this a bit quicker. So if you want to set up a Gibbs sampler for this, then the way if you remember the model that we set up, then the parameters are simple, because we have closed form matrix normal inverse V-chart equations for that one. Even if that is simple, it's still very hard to obtain a sample from the state trajectory. But now we can do this using these so-called conditional particle filters from this 2010 paper. So we started doing that. That's still fairly slow, but then together with Mike and Frederick, we figured out a way of speeding that up significantly it's a tiny little trick, but it changes quite a few things. And what that's all about, it's let me see. So what you need to do is for those of you who've seen particle filters, you have a weight and you have the sample. And if you resample the way you came from, where your parent, who your parent were, basically, then that ups the mixing significantly. That was a super short version of that, which not enough to understand that, I guess. But hopefully I conveyed the idea that you can use SMC within MCMC to get an interesting algorithm for this. So the learning will then look something like this. You just iterate using this combination of SMC and MC and update the thetas. Then you just iterate that. And there's a paper coming out soon about the details. That's on my website if you want it. And Carl has an alternative approach using variational inference. Let me show you a few examples towards the end. So this is a little toy example with some nonlinear state update in one dimension, which allows us to plot what it looks like. So if you do, we can also do maximum likelihood using this. So far I've just been talking about Bayesian, but we can also do maximum likelihood. And then the GP comes in as a regularizer, if you like. So if you just do maximum likelihood without regularization, what I'm plotting here is just the state transitions. I have xt and xt plus 1 on the axis. So that's clearly overfitting. If you then plug in the GP-inspired prior that I showed you here, you get something which is more well-behaved. And if you do the Bayesian learning using SMC and MCMC, you get something that looks like this, where you also have a representation of the posterior uncertainty. Some people prefer maximum likelihood, some prefer Bayesian. I prefer to try and do a bit of both. And I guess my prediction is that like 30 years from now, we'll see a lot of approaches using both of these in interesting ways. But that's my guess. We'll come back at DALI 30 years from now and see what happened. Here's another rather contrived benchmark that was set up some 20 years ago just in order to be tricky. So it's a nonlinear state space model in 2 dimensions. And here we compare just the RMSE with a few earlier approaches to this very problem. And you can see that it's a fair difference in both in terms of how much data we use and also in terms of the performance. And again, you can use it as a regularizer. So not necessarily for learning the full posterior, but if you just want the point estimate, you can use this to regularize, which I also find a bit interesting. Let me conclude. So what we did here was to construct the Gaussian process state space model. Alternatively, you can use this as a way of regularizing. A flexible model is indeed a good way of getting performance. I think this shows that yet another time. We need approximations of some sort. I rushed you through the way SMC can be used here, gave you an idea of how it can be used. So if you or your students want to learn more about SMC, we're giving a 1-week intensive course back in Uppsala on this in this autumn, and after that there's the SMC workshop bringing together people doing research in this area. So thanks a lot. Thank you.
Okay, I think we have time for 2 quick questions.
So regarding SMC, I mean, these guarantees are beautiful and the method has generic applicability, but somehow all these examples you find in the papers, they're all usually limited to very small dimensional cases. All the conditionals are nicely small dimensional, and then 2,000, 20,000 particles and everything works. And if you try it on 20-dimensional, 30-dimensional data, and I tried it a couple of times with those data, it just degenerates very quickly. It's just like important sampling. The guarantees are nice, but it degenerates completely to one of the particles.
Yeah, this is a very...
Something that has changed in the last few years.
Yes. So this is something that is changing quite rapidly. So yeah, maybe you want. So if you asked me this question 5 years ago, I would say, no, yeah, well, it works on up to 5-6 dimensions. I'm not sure. Maybe even 10. What we have done now is, and others, is kicking this up in higher dimensions. So we have solved problems in 1,000-dimensional state spaces. That's completely impossible with the standard algorithm. And we are still up against the cursor dimensionality, so that's not solved at all. But what has changed is that we have algorithms that change the constant in the convergence rate to the extent that you can actually run it on this thing. But that's still very much ongoing work. But I'll be happy to point you to some algorithms that can actually work in high dimensions.
I'm sure the tutorial will contain a good overview.
Yes.